this second to last video about binary trees, about trees in general, I'm going to be talking about the lookup operation on binary search trees. Before I do that, I want to talk a little bit about this function compare, which I've reproduced here, which showed up in some early day 2 or day 3, and we didn't really comment on it. We just wrote it next to like min and argmin and stuff. But I want to talk about it for a second. This compare operation takes a pair of numbers. Maybe let me format this a little better. What a relief. This compare operation takes a pair of numbers and tells you the relationship the first number has with the second number. Now, one advantage of this function is that it immediately gives you sort of complete information. Is the result less than, equal to, or greater than? And it also does it all in one go. So while it's really common to use comparisons like EQB or greater than or equal to or whatever, compare is often really nice when you want to make sure you're doing sort of the minimal work to check something like that. So here's the compare function. You can look at it. It's doing the work of sort of EQB and LEB and LTB and GEB, which we never wrote, and GTB or whatever, all at the same time. It's worth stressing that it's going to tell you the relationship the first number has with the second. So when we compare 0 and 10, we get LT, and we compare 7 and 4, we get GT, because 0 is less than 10, and because 7 is greater than 4. You can think of it as, like, if this produced a symbol, it's the symbol you would write to get the right thing. Like, this is equal, this is less than, this is greater than, whatever. Okay. So we're going to use this comparison function in our lookup function. Okay. So our lookup function is going to use the search property to rapidly find whether or not a given number is in a binary tree of maths. Now, let's go through it, and then we'll talk a little bit about some caveats here. Okay, so we look at the tree. If the tree is empty, then I can tell you up front the number you're looking for is not in the tree. There's nothing there. If the tree is a node, well, then let's look at the value of the node. Now, if they're equal, if the value you're looking for is the value at the node, we have hit the mother lode. We found what we were looking for, the needle in the haystack. Beautiful. Ride home. Triumphant heroes. Incredible. Okay, now if the number we're looking for is less than v, well then by the search property, we know that it's got to be in the left subchild. So if we get an LT, we'll just recurse and only look at the left. We're not even going to look anywhere here on the right. We just completely ignore it. Okay, similarly, if it's greater than the value at our node, well then we'll only look in the right and we'll totally ignore what's over here on the left because the search property says that's where things ought to be. So Coq accepts this function. This is totally fine. What I want to do, let's look back at my BST and my non-BST. Let's test compute lookup 5 my BST. Yeah, we got it. What about 7? What about 10? Got it. What about 20? What about 21? Okay, it seems to be giving right answers. Let's look at my non-BST. Okay, that worked. We got a right answer. Cool. What's going to happen if I write this? What answer are we going to get? Think about it. Pause the video if you need. So let's walk it through. What's it going to do? So we're going to get something like lookup 3 my non-BST. Okay, so then we're going to match. So we're going to say, well, okay, what does compare 3? So my non-BST is no. Let's print it out again. There we get to see what it is. So it's going to look at that. It's going to compare 3 1. That's going to give us greater than. So now we're going to run lookup 3 leaf 1. We're going to go straight to the right child. Why don't we look here? Well, we assumed our input had the search invariant, search property, but it doesn't. So what answer we're going to get? Well, when we look up 3 in leaf 1, we'll look at it again. We'll say, okay, compare 3, 1. That's greater than again. And now we'll get look up 3 empty. And that's going to be false. So you might look at this and be like, oh, this is dumb, right? The lookup function is clearly wrong because the number is in the tree and we didn't find it. And okay, you're right. The lookup function seems to promise to find out whether or not something is in the tree. And here it's failed, right? We had this non-BST and it didn't give us the right answer. So this is the deal with invariance. You say, look, if you give me a T that has the search property, I'm going to do a great job finding the things in your tree. I'm going to be so much faster than I could be if it weren't a search property, if it didn't have the search property, if it weren't a BST. But look, if your inputs don't satisfy the invariance, you have not met the preconditions called of my function, right? Like these are the terms. This is like the contract we enter into. If you can't give me a BST, I'm not going to promise to give you a right answer, right? My lookup function only works on binary search trees. You give me a non-search tree, all bets are off. Maybe you'll get the right answer, right? Like it's not out of the question, right? We got the right answer, but you're not in general going to get the right answer. It's like not a thing that you can expect. Okay, so invariants are great. Invariants are what let us write such a good function. Right? You might not be able to appreciate why lookup is so good. You'll definitely appreciate it by the end of CS62. So, but invariants enable us to write more efficient code. Uh, but you then have to make sure that your inputs all meet that invariant. So in the next video, I'm going to talk about some of the homework that you're doing around BSTs, and we'll talk about maintaining invariants, which is sort of the key thing that one has to do with all of the operations on refined types like binary search trees. Okay, one more video to go, and then we're done with day 7. Here, I'm going to check the box. Boom. Bazinga. Talk to you soon.